Okay, so we have a model now for handing in everything.
A model for the model.
A model for the model. Okay. So I think what we need to do is finish the basic form of the radiative transfer, and then put that in the context of the stellar atmosphere, and use something called the Eddington approximation for what's called the gray opacity approximation. So we're going to apply two things. A gray approximation, which means the opacity will be an average or a mean overall frequencies, and we'll be using something called the Eddington approximation, which has basically assumes that the specific intensity is isotropic at each layer, pretty much. That's about it. Okay, which simplifies the problem immensely. Okay, so last time we met our superheroes, we were on this page here, which had a list of the terms of the radiation field. We have I lambda, which is the specific intensity, which basically is the ergs per centimeter squared per second per steradian per unit angstrom or per unit frequency. It's a flux density, if you will, per unit solid angle. So that's I lambda. Okay, this pen is crap. And we had the mean intensity, which was the 0th moment. And we had the flux, which was the first moment. And if you remember, that went as the... I want this to be a better pen because I want this to come up on the film. Excuse me for a second, I'm going to go get some real pens.
Those jerks coffee cups.
Have you been dying to do that? You know what's still going through my head, Sean?
Oh yeah, that.
Okay. There you go. Anybody remember the name of this?
Eddington flux.
Eddington flux. This was called the momentum flux, if you will, and was related to radiation pressure. Okay, so now let's talk about the transfer equation just for a bit. Okay, basically we're going to have some kind of line of sight . We have some kind of line of sight, which we're going to have 2 points that we're going to think about. And we're going to say at this point S, you can either be absorbing light that's in this I lambda stream, right? Which means at that point you're now reducing I lambda by a bit, or you could be emitting light at that point, some of which is going in the stream, And then what you're curious about is, well, what is the resulting I lambda at S plus ds? Okay. Well, if you are talking about emission, all right, you define something called the emission coefficient such that the increment in I lambda is equal to eta lambda ds. Okay, this is called the emission coefficient, and it basically means the rate at which the energy is being emitted per unit path length, so that at S plus ds, the specific intensity has incremented by d lambda. Okay. And then you have absorption, and you say di lambda is going to be equal to chi lambda ds. Seem to have I don't have it in my notes for some reason. That's nuts. Where's the oh, I guess it's because I already introduced the absorption coefficient way back when. Yep. Okay. So you remember the opacity? The opacity is the rate at which the photons were removed from the stream per centimeter. It has unit centimeter minus 1. When you multiply it by ds, I'm forgetting something. It's proportional to I lambda. Right. Okay. Something we're not going to be talking about in this class is something called the source function. And that basically is telling you the net amount of light that's coming downstream. It's known as S lambda, and it's defined as eta lambda over chi lambda. Okay, so the ratio of the emission coefficient to the absorption coefficient, if you will, or the opacity, that ratio gives you the source function, which is basically telling you how much light is coming out downstream there. Okay. All right. Now, we are going to later be using these two quantities. We're going to be using, particularly when it comes to absorption, we're going to be using the mass absorption coefficient. So I'm going to rewrite these in terms of the density proportionalities. This is usually called little j. And then you multiply that by rho ds, and then the absorption, the opacity is usually written as the absorption coefficient kappa rho, and then you have your I lambda ds, and then here this is equal to basically j lambda over kappa lambda, because the rho's cancel out. Okay, so what I'm saying here is that the emission coefficient is equal to the emission per unit mass times the mass, and the opacity is equal to the absorption mass coefficient times the density. Okay, now the reason I'm saying this is because I think this makes a lot of sense, because this is inverse centimeters and that's centimeters. Okay. Remember, the units of kappa lambda are centimeters squared, gram minus 1. Okay? It's a cross section per unit mass. So this is the one that we're going to be using a lot. Even though if I was solving the problem in a computer on my own, I would be using this, because it's easier to use, but people haven't measured that. What people have measured or calculated is this. Okay? And sometimes they interchangeably call it the opacity, but it's not. It's the mass absorption coefficient, all right? But it gives you, in a sense, the opacity of the gas. And we're going to find out that to solve our computer model for the stellar atmosphere that we're going to be doing an interpolation on a table that has this mean mass absorption coefficient. So that's why I have to introduce it to you. All right. Now, without drawing this all on the board, this is an example of a light beam coming down S through a slab of area dA with thickness ds. The intensity is coming in and out through some solid angle, okay? And so from this, you're saying what happens across this point S to S plus ds, all right? And it turns out that you can write that equation basically the simplest form is that the net di lambda is equal to eta lambda minus chi lambda I lambda ds, all right? So the simplest form looks something like this of the transfer equation. Now, if you want the general transfer equation, we're assuming that this intensity can change also with time at different wavelengths and whatnot, then you have to take the partial with respect to time, and then you turn it into a distance by multiplying the dt by c, and you end up with this general three-dimensional equation, really, where you take the gradient of the specific intensity, you dot that into the direction s hat that you're talking about, because this is all about what happens down the line of sight, and then you take the derivative with time and you multiply that dt by c to get this, turn it into the spatial units, and you say that is equal to basically this on the other side of the equation. So instead of it being this simplified term here, you could write it as the full time changing spatial gradient. All right. All right. Okay. Now, something that I don't want to get into too heavily, but we have to think about. All right. Let's consider the one-dimensional case. Okay. And I lambda comes in, and it goes straight through the slab. Okay. And you've got your S here and your ds there, and you want to know how does the light, what's the light coming out here after L, and this is 0 coming in, okay? So this is basically the idea of what we're going to do, and you have to basically integrate this thing, d lambda ds, and integrate, okay, to get what's happening. The thing is, what if the geometry is such that the observer is not exactly downstream with respect to the coordinate system of your gas cloud? What if it's going like this? Okay, and this is the s hat direction. Okay, so in that case, basically, you have z in the k hat direction, and you have S here in the S hat direction, and the angle between them is some cosine theta. Okay? So basically now, as there's a relationship between ds and dz, okay? Let me make sure I get this right. Okay, so what's happening is it's always tricky to explain this, but your attenuation is along this path, but you want to do it in terms of the location you are in the model of your cloud. In that case, you end up having truly an S dot k hat here in front of your di lambda, because you basically are reducing it by the angle of this distance. In other words, this ds out here. Okay. So to do it along dz, you have to account for the attenuation, basically, of the I lambda. Okay. So basically, you end up with the transfer equation looking something more like this. So the reason we're doing this is we're basically saying, what is the connection between ds to the observer versus the coordinate system of the slab itself? And so we basically get cosine theta between the two here. di lambda dz is equal to I lambda. And so this becomes, if your z coordinate is not in the direction of the observer, and the theta is the angle between the observer and the coordinate system of the gas cloud, then you have to account for this cosine theta. Now, it turns out that if you divide both sides of the equation by this quantity here, okay, remember what S lambda was equal to. Okay, so if you divide both sides by this quantity here, this becomes S lambda. You get the chi over here. And so now what we're going to do is define the optical depth d tau as chi lambda dz. And that you've seen from the very beginning of the class. That was the definition of optical depth. Remember the definition of optical depth. So we replace this with d tau. And we come up with the final version of the transfer equation. Okay? So this cosine theta is taking account for any angular difference between the coordinate system and the line of sight to the observer. Okay, we have defined, and so now what we have, and I need you to understand, this is the critically important thing. that I want to say now. Okay, you might be like, okay, I've got an equation of how an increment in the specific tensity downstream has changed, but that downstream is not measured now in terms of a spatial variable. It's measured in terms of something called the optical depth. Okay, and that's related to the emissivity and the absorption at that point S minus the intensity that's hitting that point S. Okay, so obviously if there's more absorption, so that this is less than I lambda, then you get a decrement. But if there's a lot of emission in this point, such that you actually increment I lambda by a plus, then this is positive. Okay, and you have emission. Okay, fine. But the coordinate system is now optical depth. And what I want to get you to do now is to change your brain from spatial to optical depth space. Okay, now, this kind of makes sense if you think about it, because when you observe light, you're not observing its physical depth from where it came through or physical depth from where it came through. You're measuring its optical depth at each wavelength. Let's consider. There's a spectrum. Let's just do an absorption line. Normalized, okay. All right. What's the optical depth there? I don't know, a little more than 1? Does anybody remember how to read a spectrum? Hello? Okay, remember, this gets to be 0.367 or 368, whatever it was, then tau was equal to 1, e to the minus 1. What's the optical depth here? Oh, I don't know exactly, but maybe a third. You see what I'm saying? When you look at a spectrum, at each wavelength, you can read the optical depth off the spectrum. But you couldn't tell me from what physical depth in the star that was absorbed, could you? You measured light. It maps out optical depth at each wavelength. It doesn't map out the spatial depth that the photon went through. Remember what optical depth was? It's the number of mean free paths that the photon takes through the gas. Okay? It's an optical depth of 1. Well, you don't know what the gas mean free path is, so therefore you don't know the physical depth of the gas that the photon traveled through. You have to make a model to do that, but you know the optical depth. And now you have an equation as a function of optical depth at each wavelength. This isn't an individual equation solved at each separate wavelength. Okay? You now can, at least in principle, solve for this ratio to get that spectrum. Okay? Okay, great. So what we're going to do is we're going to solve the radiative transfer equation as a function of optical depth. And when we model our atmosphere, we're not going to model it in physical depth space. We're going to model it in optical depth space. And we're going to talk about, at this layer of the atmosphere, the optical depth is unity. At this layer, it's 2. All right? And so only through the model of the gas can we translate optical depth back to physical depth. Through the absorption coefficient, which means to say that if you know the optical depth at some layer in the atmosphere, you know this integral, all right, and you can determine now incrementally what the physical depth is. All right. Everybody with me? Okay. something that I don't want to do because I know all of you have had a differential equation class sometime in your career. At least I hope you have, but I think you all have. It's pretty, you know, ABC type of math to get the undergraduate degree. Therefore, you've learned about standard multiplying and integrating factors and how to carry them through to integrate an equation such as this. So basically, all I'm doing here on this page is doing your basic, you know, sixth week differential equation. How do you solve a differential equation by assuming a solution which is q lambda e to the p times tau of lambda. And you go through it and you come up with the result for the solution of this equation. I'll go ahead and write it out on the board. There it is, folks. T is a dummy integration variable. Okay, you're integrating this integral from 0 to optical depth tau. Okay, you're accounting for the fact that the optical depth is really along this line of sight, but you're using the coordinate system along this direction. So that's where you have the cosine theta term here. Okay, and here's your integral dummy term dt over cosine theta. You're integrating this. It's saying that the source function is being attenuated with e to the minus tau, and you have to integrate that along 0 to tau. All right, this is really kind of weird to think of, but it's basically saying if I start at 0, I have some source function here at 0, which is going to attenuate as e to the minus t or e to the minus tau along this path. And basically when it becomes the new s lambda here, I have to account, it's a source function, so I have to account for both the emission and the absorption. Then that is going to attenuate. So at each point here, I have e to the minus t attenuation from here to there. I have from there to there, from there to there, from there to there, from there to there, and basically at any point along here that I'm going to call tau lambda, I'm going to integrate from here to here. I have to account for attenuation of the source function from here to here, from here to there, from there to there, from there to there, and I'm integrating all that as contributions in this integral. Okay, so this one has attenuated from 0 to tau. This one is attenuated from whatever that is to there. So that's what this integral is. And then we're going to have some offset constant, which has to do with what the initial flux was coming in, this C here. Okay, so if we use the model that we're going to have some incoming I lambda here, and then some balance between absorption and emission at each point along the line of sight, then basically we have the boundary conditions, and you can then basically, the boundary condition at tau of lambda, tau equals 0 is I lambda at the surface, and so basically you get the final solution here. So basically, I lambda is coming in the beginning of it, and it's having attenuation e to the minus tau over cosine theta. So it just continues to decay along there. That's this term. And then this is the source function here, which I told you you have to integrate its attenuation to each point along the line of sight, and you get this term. If there's no emission along the line of sight, guess what you get? Okay? So all semester we've been talking about pure absorption, right? If there's no emission anywhere, this is 0, the source function is 0, this term is 0, and basically you have no source function in the gas doing any emitting on its own. I lambda comes in and you basically get the e to the minus tau attenuation, okay? What tau is actually in this coordinate system, related to this coordinate system z, so we have a cosine theta to allow for the relationship between the spatial and the direction to the observer. Okay. In intergalactic medium work, we never worry about this geometric factor. We just assume the cloud is some slab and we give its coordinate system along the line of sight. With a star, we can't do this because a star is a spherical structure. So sometimes, if you have z coming out of the star, the normal of the star is in the line of sight direction. But over here, around the corner, toward the limb, you're looking at photons that are actually coming out at an angle relative to the z, the vertical coordinate of the star. Okay? So that's why we need this cosine theta. We'll get into it. So here is my explanation of the two terms. I'm not going to go into any more detail than I did here, but you can see that if you have the e to the minus tau, for the different taus, this is how the intensity decays. What you're really doing are accounting for these various different source functions at different locations that you have to then account for the attenuation of the source function from here to here, the source function at this point from here to here, and you have to integrate all those contributions and you get this term. Okay? All right. Then for fun, I'm not going to do this. You can study this page. Basically, I assume a very, very simple model, and I make illustrations of how the source function changes pure absorption. So you're welcome to look at that. It's a simple model for helping you understand more intuitively what the source function does and how it behaves. Okay. I've had homework problems in the past where I have people work those things out. Okay. Are there any questions on that before we move to the next little segment? Okay. So this equation here is based upon the observer being on the L side and the incident side being at 0. That's the form of the equation you get. Okay. What we're going to find out when we get that's so, and people write the general form of the radiative transfer equation as that solution, because this is the most typical astronomical type of setting, or I should say configuration, that people adopt, except if you're doing stars. Okay? If you're doing stars, people will do it differently. And so that's what I want to talk about next. Now, do you remember when we went through atoms? Okay, we went through the atoms, and one of the things I showed you was how you got the emission and the absorption coefficients from the Einstein A coefficients and B coefficients. So you may not remember it, but I went through it already. So I have it in the notes here again in handwritten form, but I'm not going to cover it again. Okay? But you'll remember that basically we found out that the Einstein A's we're related to these overlap integrals from the atomic physics, and so that is, you know, when you want to know where does the real source function comes from, you got to go all the way back to that atomic physics, okay, and how those Einstein A coefficients are created, how they come out of the quantum mechanics, and then it turns out that you multiply the Einstein A by h nu, then you divide by 4 pi, and guess what? You get the emission coefficient. Simple things like that. And so that's what all of these notes are right here, is basically writing those out again for you, and then some more discussion about how you can actually write these out in terms of the transfer equation. Here's the Einstein A and B relationships again. And I basically am trying to eventually show you, okay, that if you carry through the assumption of thermal equilibrium, I'm on now the source function, that you can show that the source function is actually equal to the Planck function, okay, in thermal equilibrium. Okay. This is in 1,000 books. This can be this can be studied and looked at in any number of books. I've summarized it here in a way I hope is, you know, as clear as, or clearer, I hope, than any of the other books. But again, you know, we all have different minds, and the way so-and-so does it resonates with our brain better than the way such and such does it. So we all have our favorite author and our favorite books. Okay, that's great, but here it is once again, standard stuff showing you that in terms of the A and the B coefficients, and assuming the Boltzmann equation of excitation equilibrium and thermal equilibrium, you can show that the source function ends up being the Planck function. Okay? It's a nice derivation. And then this statement here on this page, the last page of this segment, is basically saying that if you have thermal equilibrium, that the integrated energy per volume per unit time that's emitted, which is given by this integral here, which is the emissivity over all solid angles, integrated over all frequencies, is equal to the integrated energy per unit volume per unit time that's absorbed, which is basically kappa I nu, okay, or chi actually. And so when you carry through these integrals, you end up with this integral here, and you can basically show that for this equality to hold, that the integrands have to be equal to one another. And so by showing that, you show basically that the source function in thermal equilibrium is the same thing as the mean intensity. Okay, so now in thermal equilibrium you've shown two things about the source function. It's equal to the Planck function, and it also is the mean intensity. Well, guess what? In an isotropic situation, if you remember right, we said that the mean intensity and the specific intensity were the same. So let me write this down for you now. Let me summarize this. Condition 1, thermal equilibrium. We get that the source function is equal to the Planck function. And we get that the mean intensity is equal to the source function is equal to the Planck function. Okay. That's in thermal equilibrium. Now, if we also an isotropic I lambda, which means that no matter what direction you look in theta lambda, okay, it's the same specific magnitude of the same specific intensity. We have that J lambda equaled I lambda. That was from our previous derivations. Okay. Well, that means if both conditions hold, life is extremely simple. Now we know both conditions don't hold. So now I want you to understand this. You have thermal equilibrium. The source function can be shown to be equal to the Planck function. And because of conservation of energy per unit time per unit volume in thermal equilibrium, the mu intensity is equal to the source function is equal to the Planck function. Now, if you also have an isotropic specific intensity, we were able to show through taking the zeroth moment of this that J lambda equaled I lambda. So therefore, in thermal equilibrium with isotropy, I lambda is equal to the Planck function. Okay? Now that's going to be very important because we're going to engage in our next lecture on the layers of the atmosphere, and we're going to apply two things. So let me write this down for you, what we're going to apply. We are going to apply, number one, isotropy to solve the atmosphere. That means, well, we're going to apply that. Okay? And number two, we're going to simplify by assuming that we have a mean we're going to have a mean opacity, which is going to be related to the temperature gradient of the specific intensity, okay? And this is going to be called, it's called the Roslin mean when you weight it this way. But what we're going to do is this is called the Gray approximation. So we're going to assume isotropy and thermal equilibrium, and we're going to simplify by assuming the Gray approximation, which is to say, we're going to take out the wavelength or frequency dependence of the opacity or the absorption coefficient. We're going to compute a mean that we're going to say applies at all wavelengths. It's called the Gray approximation. So when we meet next, we are going to talk about the plane parallel approximation for the atmosphere and fix the geometry so that our transfer equation applies properly. We're then going to apply these two approximations, which is going to lead us to what's called the Eddington approximation of the atmosphere, for which we will derive a very simple formula. And let me give you the punchline now, since I've got you. And actually, on the notes, call this the punchline. And I just want to make sure I get it right. But I think it's something like 3/4 times T effective to the fourth. I'm almost there. Okay, in the next set of notes, it's quite a ways in. There's a set of notes that says the punchline. I'm just going to give it to you now for fun. we're going to be able to solve the radiative equations using a mean opacity, and it's going to show us that the temperature going as a function of optical depth into the atmosphere goes as this relationship right here. So the beautiful thing now is you're going to solve your atmosphere as a function of tau, and that's your independent variable. You put that in. I'm going to solve my atmosphere, and I'm going to go from tau equals 0.001 to tau equals 100. That's my coordinate system into my atmosphere. And so you vary this number. From it, you calculate T, so now you have your temperature profile as a function of optical depth into your atmosphere. Boom! The next step now is just to solve the pressure gradient. And now you have T and P at each layer. And you know how to calculate the gas balance if you have T and P. At least you will be when you're done with this homework assignment. Okay? So what I'm trying to do is hopefully alleviate some of the anxiety about the uncertainty things that are coming into the model. In the end, we're gonna take this stuff, we're gonna reel it in to this. Okay? We're gonna reel it into this, and you're just gonna solve your atmosphere as a function of tau. You've got the temperature profile, and then I'll just give you the little formula on how you solve for the pressure gradient, and you're done. So once you get this homework done, it's not going to be, it's not, in a sense, going from problem 2 of this homework to problem 3 is very similar as like going from problem 3 to making the stellar model. Because problem 2 is you solve everything at one temperature. Problem 3, you put a temperature loop around it. Okay, well, the atmosphere is problem 2 with a temperature as a function of some variable. So you solve it as a function of T. Okay, now you know how to do it at fixed pressure, so you just have to add one more loop around it in a sense for the pressure. So that's why the homework is designed to do this stepping stone. Maybe it's clear what's, at the end of the semester you all make recommendations. More of this, less of that, you might make the recommendation. Have problems earlier in the semester. I used to actually teach a class where I had that problem set at the very beginning of the semester, and then people sat on it for 5 weeks and didn't touch it again. But I decided to do it backwards this time. Maybe it's not good to do it backwards. Maybe you feel more comfortable solving it earlier in the semester. If you go upstairs and ask Jacob, when did you do this problem? He'll say, oh, we did that like on the 3rd week. So, feedback's good. Always get better at it. Listen to the previous students, adjust. The next set of students say, no. So, and then I get old enough to retire. So anyway, like I said, we're going to reel all this into this simple equation, and then I'm going to show you how to wrap it into the pressure gradient. Boom.